Hello everyone. Experiment number 2 is about sampling and Nyquist frequency. Assume that we have a sinusoidal signal with a period of t and a frequency of 1 over t. And assume that this signal is going to be sampled by a sampling frequency of f of s. So these are the samples, and the interval between each sample is ts, so f of s is 1 over ts. Based on the Nyquist theorem, the relation between f of s, the sampling frequency, and f, the frequency of the signal, should be this f of s at least should be greater than 2 f of max, which is in this case is f, in order to be able to recover the signal from the samples. So if these are the samples, we are going to connect them together to get the signals, let's say, back. In order to be able to recover the signal, the sampling frequency should be at least twice the maximum of the frequency in the signal. So in this experiment we are going to prove that using the DSP board. So on the first part, what we do, we consider the A to D. So the signal is coming to the ADC on DSP board, and then we are going to connect it to the DAC, and we are going to observe the output. So this input is coming from the function generator, so we are going to connect this to the function generator, and the ADC is going to sample the signal. So assume that this signal is going to ADC and it's going to be sampled, and of course we're going to have the samples here, and the DAC is going to put back these samples together to create a sinusoidal signal again. So this is going to be output. So based on the Nyquist theorem, if the sampling frequency f of s is set properly in ADC and the DSP board, if you double click on the ADC block on your model, then one of the parameters that you can fix is the sampling frequency. So we're going to change the sampling frequency in this experiment to different values. The values could be 4K, 8K, 16K, and different things. And we are going to see if we are able to create this output signal so that output and input are matching here. So we're going to see if this output is going to match the input. If the output is not matched to the input, it means that the sampling frequency here was not selected properly. So this is what we are going in this experiment. In the design part, what we are going to do is to find out the harmonics of the input signal. In order to define the harmonics of the signal, we are going to connect our function generator to ADC block, and after ADC we are going to design a filter, and then the output of filter is going to DAC, and the DAC is going to create the output, which is going to be our oscilloscope. So a scope is used to measure the output signal here. So what we do, we are going to design this filter. If you design the filter in a way that harmonic is going to be filtered, the first harmonic, second harmonic, so it's obvious that if the function generator has, let's say, square wave input. If you get the first harmonic, so if you filter the signal so that first harmonic is going to be extracted and is going to be here, then you should be able to see a sinusoidal signal on the scope. Why? Because the Fourier series says that a square wave signal is made of a lot of different sinusoidal signal. So you add like if you recall the Fourier series, a lot of sine and cosine signals going to be added together to create the signal x of t. So first harmonic could be extracted if you design a filter properly, so that the first harmonic, I'm going to call it F1, is going to be like visualized on the scope here. So that's for the design activity. In order to do that, you need to be able to work with like a wizard. It's called filter wizard and filter tool. It's called FDA tool. So what you do, you have to type FDA tools in MATLAB command, and then the following wizard is gonna pop up. In this pop-up, first you define the type of filter. So you have the option of low pass, high pass, band stop. So everything you can define it here. So let's define a low pass, and then you have the design method option, which could be IIR filter or FIR filter. So let's design IIR, and there are different methods: Butterworth, Chebyshev type 1, Chebyshev type 2, elliptic, and other methods. So I'm going to select the Butterworth. In this experiment, you can define just Butterworth, whatever is your option, but next experiment you have to define and experiment different design methods. Then is the order of the filter. So you can just simply go by the default, which is the minimum order, or you can design a specify, like you can specify the order 10 to whatever. So for now I'm going to go with the default, which is the minimum order. Another option is that you want to define match exactly what, a stop band to be matched or pass band. Here for low pass filter, a stop band should be fine. The frequency spec is very important. Basically the filter parameter is defined here. The units could be hertz or normalized. For now I keep it to hertz. Make sure the sampling frequency Fs is set to 8000 for this experiment, because we are using the sampling frequency of 8000 for our A to D. Fpass, and if you don't know what Fpass is, you can look at this diagram here, and it would tell you that Fpass is basically the frequency from 0 to Fpass is the passing band, and Fstop is going to be the frequency at which the A stop holds. It means that the gain is going to be A stop at F stop, and the gain is going to be A pass for F pass. So I want a low pass filter that only passes from 0 to 1000 hertz or 1 kilohertz. I want the F stop to be 2000 hertz. It means that A stop, which is related to F stop, is 80, and the unit is dB. So it means that at 2 kilohertz it's going to be attenuated by 80 dB. So the best bet is just for me now to click on the design filter, and then the graph is going to show up here, and maybe we can understand the parameter better on the graph. So you can see that it is a low pass filter. Why? Because it's passing the lower frequency at this point, and as the frequency is going higher and higher, the attenuation is getting higher and higher. It means that it's not quite passing the high frequency. And then you can see that the parameters that we had for a stop to be like 80 at 1 kilohertz is the stop band, so it's the frequency that the filter stop to pass from 1 kilohertz. At 2 kilohertz we define 80 to be a stop, the gain at a stop, so that's why you see minus 80 dB at 2 kilohertz. So if you want different parameters, different stop band or different pass bands or different gains, you just play with the parameters in the FDA tool wizard. At this point you have to click on realize model. So when you realize the model, assuming that you had already a model open, then you can see that the filter block is created. It says filter, so it has an input, it has an output. So we assume that the input is connected to your A to D block here, and the output is probably going to the DAC module block on the 6713 model that you have created based on the knowledge that you had from the first experiment. So this is the way that you create a filter and you export it into a model, into a Simulink model. This is the connection for this experiment. This is your DSP board. So your DSP board is here, 6713 DSP board. If you look, there are two jacks here, the first one and the second one. This is your line in. This is your line out. Basically, line in is the terminal, the audio jack where you connect your signal to. So that's why it's going to the function generator. So if you look at here, the function generator is going here. So you connect the line in to your function generator. And the other jack is called line out, which is the output processed by DSP 6713. So the signal which is coming from the function generator is going to be processed, and then it's going to be sent out to line out. So that's why this signal is coming to the channel 2. So this is basically going to channel 2 on the scope. Why? Because we want to monitor it. And also we are going to tap from our function generator and connect it to channel 1. So this is the channel 1. Why? Because we want to be able to see the input and output both on the oscilloscope. So what happens, you change the frequency here. So this is to change the frequency up and down. And let's say if you have a sinusoidal signal at the input going to the board, if it is a low pass filter, you expect to see the output. Let me change it to a different color. So you expect to see the sinusoidal signal, and when you increase your frequency, so and you have designed already a low pass frequency, you're gonna see either no signal or a very attenuated signal, because the low pass filter is not passing the higher frequency with the proper gain. And this is the way that you can find out about low pass frequencies. Or if you want to extract the harmonics, you have to think of how to define a low pass filter or a band pass filter to extract the first harmonic. This is something that you have to figure out on your own. This is all about experiment number 1, and I hope you were able to catch enough material to do the experiment without any problem. Thank you.